CNC programmers play a vital role in the manufacturing industry by converting engineering drawings into precise machining instructions using computer numerical control systems. They require strong knowledge of G-code, CAM software, and a keen eye for accuracy. This script outlines essential interview questions and answers that demonstrate practical skills, software proficiency, and real-world problem-solving needed in this technical role. 1. What are the core responsibilities of a CNC programmer in a manufacturing environment? The responsibilities of a CNC programmer revolve around transforming technical designs into efficient machining instructions. A CNC programmer interprets engineering blueprints and selects the proper tools, materials, and machining processes for the job. They utilize CAM software to generate accurate toolpaths and export G-code for CNC machines. Their work includes setting up machining parameters such as spindle speed, feed rate, and cutting depth. CNC programmers are also responsible for conducting dry runs and simulations to validate programs before production. They collaborate closely with machinists, engineers, and quality control teams to ensure the part meets specifications. Additionally, they troubleshoot any machining errors and revise the code when necessary to improve productivity and reduce material waste. Their role demands high precision, attention to detail, and continuous monitoring of machining performance. They must keep documentation updated, stay current on technological advancements, and maintain compliance with safety standards. Overall, their contributions ensure the consistent production of high-quality parts with minimal rework or downtime. 2. How do you approach writing a CNC program from a technical drawing or blueprint? Writing a CNC program from a blueprint begins with a detailed analysis of the technical drawing. First, the CNC programmer studies the part dimensions, tolerances, surface finishes, and material specifications. Identifying critical features like bores, slots, threads, and contours helps determine the machining sequence. The next step involves selecting the correct machine and CAM software. The programmer chooses suitable cutting tools and fixturing methods based on the geometry and material type. After defining the work coordinate system and origin point, the programmer begins creating the toolpaths in the CAM system, ensuring optimized tool movements to reduce machining time. Once toolpaths are generated, post-processing converts them into G-code tailored to the specific CNC machine. The program is reviewed for errors, and simulations are run to verify accuracy. Any collision risks or feed rate issues are corrected. Once validated, the program is transferred to the machine where a dry run is performed with the tool above the workpiece. After final verification, production begins. Thorough documentation and program backup are also part of the workflow. This structured method ensures precision, efficiency, and safety during manufacturing. 3. Which CAM software tools are you most experienced with and how do you utilize them? A CNC programmer's effectiveness is greatly enhanced by familiarity with top-tier CAM software. Proficiency in tools such as Mastercam, Fusion 360, Solid CAM, or Siemens NX enables efficient program development. Personally, I have hands-on experience with Mastercam and Fusion 360. I utilize Mastercam for complex multi-axis toolpaths and surface machining. It allows me to import CAD files, define machining operations, and optimize toolpaths with features like rest machining and dynamic milling. Fusion 360 is particularly useful for cloud-based collaboration and integrated CAD/CAM workflows. I use it to create adaptive toolpaths, simulate real-time cutting, and manage multiple versions of the program. When starting a project, I import the 3D model or drawing, set up the stock dimensions, and define the work coordinate system. I then choose tools from the database, specify spindle speed, feed rate, and cutting strategy. After toolpath creation, I run simulations to detect errors and perform post-processing to generate machine-specific G-code. These software platforms streamline the workflow, reduce programming time, and improve the accuracy of complex parts. Keeping up to date with the latest versions and features is also essential for maximizing performance. 4. What steps do you take to ensure CNC programs are error-free before production? Preventing errors before a CNC program goes live is critical to avoid costly mistakes. My error checking process begins with meticulous code review within the CAM environment. After generating toolpaths, I simulate the entire machining process to verify tool movement, detect possible collisions, and assess machining time. I examine critical areas such as rapid moves near part boundaries, incorrect tool clearances, and improper spindle speeds or feed rates. If I notice any deviation from tolerances or surface finish requirements, I revise the operation parameters. I also double-check tool selections, stock setup, and the work offset coordinates. For multi-axis machines, I confirm axis synchronization and clearance planes. After simulation, I perform a dry run on the machine with the tool raised above the part to watch real-time behavior. I monitor axis movement, tool changes, and cycle times. During the first physical run, I machine a test piece or use low-cost material to confirm program accuracy. Feedback from machinists is also considered to fine-tune the program. All these steps collectively help eliminate errors, ensure dimensional accuracy, and maintain high production standards. 5. Describe your experience with G-code and M-code programming. G-code and M-code are the foundational languages of CNC machines. I am well-versed in both, and I frequently use them for customizing and troubleshooting programs. G-code commands define specific movements and actions like linear motion, G01, rapid positioning, G00, circular interpolation, G2G03, and setting offsets, G54, G59. M-codes handle auxiliary functions such as starting or stopping the spindle, M03, M05, coolant control, M08, M09, and tool changes, M06. In my workflow, I often review and manually edit the generated G-code to refine operations, reduce unnecessary movements, and enhance cycle efficiency. For instance, I adjust G41, G42 cutter compensation or G43 tool length offsets for better accuracy. When post-processing fails to handle a custom machining sequence, I insert custom G-code and M-code instructions manually. I've used code macros to automate repetitive tasks and subroutines for complex patterns. Understanding these codes gives me greater control over the machine and helps in diagnosing issues quickly. It also enables communication with machinists who rely on these codes for setup and operation. My expertise allows me to strike a balance between automated programming and manual fine-tuning to optimize part quality and machining time. 6. How do you optimize tool paths for efficiency without compromising accuracy? Optimizing tool paths is a key part of CNC programming that balances efficiency with precision. I begin by analyzing the part geometry to identify the most logical sequence of operations that minimize tool changes and movement. In the CAM software, I enable high-speed machining strategies such as adaptive clearing, which maintains consistent tool engagement and reduces machining time. I also use rest machining to focus only on uncut material during subsequent passes. Toolpath overlap, entry/exit points, and retraction distances are minimized to ensure smooth transitions. I select tools based on cutting capabilities and adjust feed rates according to material type and tool geometry. For finishing operations, I apply tighter tolerances and reduced feed rates, ensuring surface quality and dimensional accuracy. Where feasible, I combine roughing and finishing in fewer steps to save time. Simulations help validate these optimizations before running on the machine. Additionally, I monitor tool wear and spindle load data to make informed adjustments for future runs. These strategies collectively enhance cycle times without sacrificing the part's critical dimensions or surface finish. 7. How do you handle machining a complex part with tight tolerances? Machining a complex part with tight tolerances requires a disciplined approach from setup to final inspection. I begin by carefully reviewing the engineering drawing and identifying critical tolerance zones. I then select the appropriate CNC machine that can deliver the required precision. Next, I choose cutting tools with high rigidity and wear resistance and set precise tool offsets. In the CAM software, I define accurate tool paths using finishing strategies like contouring or scallop finishing with reduced stepovers. I maintain lower feed rates and RPMs during finishing to minimize tool deflection. The workpiece is securely fixtured to prevent vibration, and thermal compensation is applied if needed. After programming, I simulate the part and then perform a dry run. For the initial part, I use in-process inspection tools like dial indicators and CMMS to validate the results. If tolerances are not met, I revise the program and retest. I log all measurements and adjust the program for tool wear or thermal drift. My attention to detail during each phase ensures that even the most intricate parts are machined to specification. 8. What challenges have you faced when programming for multi-axis CNC machines? Programming for multi-axis CNC machines presents unique challenges like tool interference, axis coordination, and maintaining part orientation. One major difficulty is visualizing complex tool paths in a 3D space, especially when working with 4-axis or 5-axis simultaneous movements. To address this, I rely heavily on advanced simulation within CAM software to detect any potential collisions or overtravel. Post-processor accuracy is another challenge. Using a customized post-processor tailored for the specific machine ensures accurate G-code output. Defining correct tool tilt angles, rotary positions, and clearance planes also requires careful planning. Another challenge is programming for undercuts or compound angles which traditional 3-axis setups cannot handle. I solve this by breaking operations into index steps or using specialized tooling. Fixture design must allow for unrestricted tool access while keeping the workpiece secure. Additionally, axis limitations and machine calibration need to be considered to avoid movement beyond machine capacity. Effective coordination between the A, B, and C axes is essential to avoid singularities or positioning errors. These challenges demand deep technical knowledge, creativity, and attention to simulation feedback. 9. How do you ensure tooling selection aligns with machining requirements? Tooling selection is vital for successful machining. My approach begins with analyzing the material type, part geometry, and tolerance specifications. I match cutting tools to the hardness and machinability of the material. For example, I use carbide end mills for hardened steel and high-speed steel for aluminum. I also consider tool diameter, flute count, coating, and length to ensure rigidity and chip evacuation. I select tools from a verified library in CAM software and cross-reference manufacturer recommendations for speeds and feeds. For parts with deep cavities or fine detail, I choose tools with extended reach and small diameters, making sure to apply gradual step-downs to reduce tool stress. I plan tool changes logically to minimize machine downtime. I also factor in coolant compatibility and spindle speed limitations of the CNC machine. After selecting tools, I simulate the process and monitor cutting performance during test runs. Any chatter, tool wear, or breakage prompts me to revise the tool selection or feeds. Proper tooling ensures the desired surface finish, dimensional accuracy, and process reliability. I match tools to material and part geometry using manufacturer specs, verifying in CAM software, and testing performance for optimal machining. 10. What methods do you use to troubleshoot CNC programming or machining errors? Troubleshooting errors in CNC programming or machining involves both analytical thinking and hands-on testing. When a machining error occurs, I first observe the machine behavior during operation. I check for alarms, unexpected movements, or dimensional inaccuracies. Then I review the G-code line by line to identify potential logic or syntax errors. I rerun the simulation in CAM software to verify toolpath accuracy and check for any overlooked collision or overtravel. I inspect the physical setup, including work offsets, tool offsets, fixturing, and material alignment. If needed, I re-zero the machine or recalibrate the probe. I also evaluate tool wear and ensure tools are correctly loaded in the carousel. When the issue is mechanical, I coordinate with maintenance to inspect for backlash or spindle alignment issues. For surface defects or poor finishes, I adjust speeds, feeds, or coolant flow. I keep logs of all errors and resolutions for future reference. Effective communication with machinists helps in understanding recurring issues and applying permanent fixes. I analyze machine behavior, check code, resimulate, inspect setup and tooling, and adjust machining parameters to solve errors efficiently. Mastering CNC programming requires more than just software knowledge. It demands precision, troubleshooting ability, and continuous improvement. These 10 essential questions prepare candidates to demonstrate their full skill set and approach to real-world challenges in CNC programming.